So we will start off today with Cecile Chevrier. I've started to learn it. And she is a main researcher here at ISEE and Inserm. And she has a large expertise on environmental chemicals and multiple health outcomes. She's also has a large team on in epidemiology here, and she has also started up the CEPAGE cohort, which is an amazing source. But she's also, within the French context, has contributed as a scientific expert in new policy actions. So that's, I think she will start today. And I've heard also that she will be the future French artist. So, so the floor is yours.
So thank you very much for this invitation. It's an honor for me to have this opportunity to talk about pesticides and child health. But the idea today is not to be exhaustive on this topic, but to provide you some examples of what we can do as epidemiologists on this topic, what type of studies we can use, designs and tools. And I will also try to describe what we did with our scientific results, how our scientific evidence has turned into a possible policy action. But please note that it's a very personal point of view. And it's also very focused on the French context, which is my main study area for pesticides. And you will see that France is quite rich in terms of people, national agency, local organization that work or deal with the risk of pesticides for health, environment, and ecosystem. So I will show you some initiatives that we had recently in France. Okay, so let's start with an overview on pesticides. So pesticides are used worldwide to control and destroy living organisms, which we think that harmful for our human activities. They are mostly used in agriculture to increase our food production, but they have also been used in different other types of area. For instance, in several types of industries, such as wood industries, transport industries. We also use pesticides in our urban areas, for instance, when we want to treat some garden parks or sport fields, golf fields, and so on. And we have also some individual use in our domestic context to deal with some pests in our homes, gardens. And it's also very useful in some specific area to fight against vector-borne disease. So pesticide, sorry, we have several types of languages when we talked about pesticides. And the most common one is driven by the target. Sorry. I need to remove something here. Yes. Yes. So for instance, we talked about herbicides to fight against weeds, insecticides for insects, fungicides for fungi, bactericides for bacteria, and so on. And we have also in Europe a language which is driven by our regulation. So in our regulation, we are referring to a plant protection product for all the pesticides that we are using on our plants, on our garden. And we have also a regulation for biocides, which refer to all the other products that can affect or kill biological organisms. So pesticides exist since the early stage of agriculture, and the first synthesized chemicals came on the market as pesticide in the 1940s. With, for instance, I don't know if you can see correctly, but organochlorine here. Organochlorine insecticides, which dominated the market at that time, but because of their high persistence in the environment, they were then replaced by organophosphate, here, or then pyrethroid and neonicotinoids insecticides. Thank you. And then in the early 50s, There were a quite intense chemical innovation and new pesticides. It's very loud. New pesticides were regularly introduced on the market. And the most innovation came with a decreased application rate, meaning that we reduced the quantity of pesticides that we wanted to put on the crops. And with that, we also observed an increased bioefficacy of the substance, conducing to possible concerns for the non-target species, especially if the substance is transferring to different compartments of our environment. Is it too low? That's okay. So use of pesticides became clearly worldwide in the early 50s. And today we estimated around 600 synthetic active substances with 4 million tons of pesticides in 2016, and it's probably higher now. And then the history has changed for the last 2 or 3 decades. So the number of new pesticides declines with less chemical innovation by the industries, because it has become more and more expensive and long to put and to develop and to put the pesticides on the market. For instance, in Europe, it's about 10 years today to put the pesticides, to develop and then register and put the pesticide on the market. And so as a possible consequence in Europe, we estimate that about 10% of the market are illegal pesticides. That's for you, Jade. Okay, so France has an important agricultural activity. So half of the area is dedicated to agriculture. We have a lot of cattle, also porks and poultry. And so different types of cereal crops that are needed to feed the animals. And cereal crops require generally herbicides and fungicides, but also sometimes insecticides. We have also fruits and vegetables that require different types of pesticides. And we have vineyards that use a lot of fungicides, but also herbicides and insecticides, and mostly in the south of France. So finally, we use about 70,000 tons of pesticides, mostly herbicides and fungicides, but also insecticides. And we estimated today about less of 300 substances authorized on our market for our plant protection. Okay, so in terms of non-agricultural activities in France, so recently, thanks to a recent national survey conducted by ANSES, which is our National Agency for Safety and Risk Assessment, we know that French population has regular domestic uses of pesticide products at home. And it's mostly against insects, but among insects, it's mostly against fleas and ticks because we have a lot of domestic animals at home. And we also shown in this survey that we store a lot of products at home, and most of these products contain pyrethroid insecticides, some of them glyphosate, that you should have heard about that. And also for a quarter of products forbidden, they contain banned molecules. So after this survey, we had a national campaign to sensibilize the general population not to store our domestic products too much longer. And then concerning our park, the use of pesticides on parks, roads, gardens, or other publicly areas, France has recently introduced a progressive phase out of pesticides in these publicly areas, but also in our private gardens, meaning that we could no longer use pesticides for the maintenance of these public spaces, forests, roadsides, most of our sport and golf fields and so on. And the quantities of pesticides for these non-agricultural areas in France have been divided by 5 just in a few years. And everybody feels good with that, or almost everybody, meaning that finally these issues maybe are not so essential. And finally, we have also uses of mostly insecticides for vector control actions and in our industrial use, and especially wood. Okay, so in France, we have a lot of data, and we have accumulated a very huge amount of data for several decades, stating that our environment is largely contaminated by pesticides. And we go quite quickly for that. Maybe I guess you should know some of these results. For water, it's well monitored in Europe, so we all know that most of our water contain pesticide residue. In France, we say each year that 80% of our ground and surface water contain pesticide residue, mostly herbicides, but also banned substances. For soil, there is no systematic monitoring, but several academic studies show that 80% of soil had pesticide residues, diverse type of pesticides, and whatever the area within crops or outside crops. For air in France, we had a recent national monitoring, again conducted by ANSES, our National Agency for Risk Assessment and Safety, that showed that air samples were all contaminated by pesticide residues. And again, whatever the area, urban area, rural area, and so on, and whatever the season. And here we found fungicides, herbicides, and banned insecticides. We found pesticide residues in our food, and ANSES, again, conducted several total diet studies in France. So they measured a lot of pesticide substance in a lot of food items that should reflect what we eat in France. And we show that we had pesticide residue detected in almost 40% of our food items in Europe, in France, sorry, and mostly insecticides and fungicides. And our indoor environment is also of concern. So here there is no systematic monitoring, but we have punctual studies, and we showed a frequent contamination of our indoor compartment from air samples or dust samples by both types of pesticides, agricultural or non-agricultural pesticides, for instance, here. On indoor here, we found permethrin. Permethrin is a pyrethroid insecticide, which is not allowed for agricultural uses, but we found permethrin in all of our homes. And glyphosate here, that we found in all of our homes, urban homes or rural homes, and this is a study conducted in Britain. Okay, so to finish this big picture of pesticides in France, it's not surprising to observe that the general population is exposed to pesticides. And this has been shown by academic research, and then also by the result of our human biomonitoring strategy handled by Santé Publique France. So using urine samples of French pregnant women, for instance, in 2011, they found pyrethroid and organophosphorus insecticides as dominant molecules in the urine. And a few years later, they observed the same gradient, pyrethroid and OP insecticides. And the striking results here is that they observed a higher urinary concentration in children for pyrethroid and OP. And the problem here is that we have not yet identified the possible exposure sources, explaining why this level is higher for children. We might think, for instance, to the indoor environment with the permethrin, but there is still a gap of knowledge here. Okay, so why children's health should have a specific attention? Just in case you don't know, children are not little adults. No, it seems obvious for you, but a few centuries ago, as you see, we represented a child as a little adult with a smaller head that it should have had. So a child is building a body for a lifetime. He has higher needs of water, nutrient, and oxygen, so he may be more exposed to toxicants by ingestion, inhalation, and so on. He has immature physiological system, endocrine system, metabolism, detoxification processes, meaning that children might be more vulnerable to toxicants. And children also have specific behavior, the head and mouth behavior, and also he has a specific exposure from in utero life and also with breastfeeding. So when we work on the risk factor of child health, we say that the timing of exposure, the window of exposure is important. And this is a DOHAT concept that say that there are developmental origins of health and disease. And the pregnancy and the first 2 years of the childhood, meaning the first 1,000 days, are identified as the crucial developmental periods within these concepts. It means that a stressor early in life might induce little things, little responses, subtle responses that we cannot, that might be not visible as a clinical endpoint, that then might conduce to major health alterations or diseases later in life. And so these little things matter. It matters for the individuals, but it matters also for the public health. At population scales, we say that it might induce major public health impact. And this has been clearly illustrated by Bruce Lanphier about the loss of IQ due to neurotoxicants such as lead. For instance, studies in USA, where is it? It's here. Studies say that the current level of lead exposure among children in the US conduces to a decrease of 5 IQ points on average, meaning that in the ideal situation, we should have on average 100 points. With a decrease of 5 points, it means that there is a shift of the global distribution of 5 points to the left, meaning that we have a bigger, finally, I can't see my we have a bigger number of challenged children with a lower IQ from 6 million in the ideal situation to 9.4 million in the current situation. Okay, so just key messages for the first part. Pesticides are mostly used in agriculture, but there are also other uses, and some of them being non-essential. Modern pesticides are more bioeffective today, but present in our environments. So what about the non-target species, especially if these substances is traveling in our environment? Pregnancy, or at least the first 1,000 days, are crucial periods for human health. Pregnant women and children are exposed to diverse pesticides. So we need observational evidence to study the potential adverse impact on child health of this exposure to pesticides. Okay. It's not so sad. Okay, so according to the DOHAT concepts, the best study design is to conduct a longitudinal study on the pregnancy with prospective and repeated data collection of multiple data, including biobanks, in which we can do chemical analysis, chemical measurement of any kind of chemical substances. So this is what we did in Brittany with some of my colleagues. We followed pregnant women from 2002 to 2006, and then we followed the children at birth and at different ages. And we are still continuing the follow-up with Charlene and Christine. And at the start of our cohort, there were several first signals suggesting that we should investigate the possible role of organophosphorus insecticides, the OP insecticide on child health, because at that time we had various and common usages of OP insecticides, both in agricultural and domestic areas. And in animal, there were studies suggesting neurodevelopmental toxicity, and in humans, the acute neurotoxicity was well established. And a few years later, in 2009, we also had first epidemiological evidence from good quality mother-child cohort, all coming from the North America context, and that showed decrease in birth weight, decrease in head circumference, decrease in the cognitive performance of the children, in association with prenatal exposure to OP, measured by biomonitoring, chlorpyrifos assessed in blood, or dialkyl phosphate, which are the OP metabolites that we can find in the urine samples. So in pelagy, we conducted similar study with similar tools. We had the same question. So we measured metabolites of OP insecticides. No, my mouse is here. Okay. We measured metabolite of OP insecticides with our urinary dialkyl phosphates in the urine samples collected at birth. We also conducted a neuropsychological follow-up of our children at 6 years old with a standardized neuropsychological battery test. For instance, a global intelligence scale we call WISCs for children. And we then complete our follow-up with brain imaging of our children, for a subgroup of the first children that has participated to the neuropsychological follow-up. So what did we find in our pelagic cohort? So we found, we observed a decrease in birth weight in association with increasing urinary concentration of metabolite of OP. And as you can see here, we have a decrease of about 100 grams of the birth weight for the last tercile of exposure compared to the first tercile. So this is this little thing that matters. With a PhD student, we then showed no association between our prenatal exposure to OP measured in urine and the cognitive score that we have assessed at 6 years old. And then with another PhD student, we look at the brain imaging and especially with the functional aspect of the brain imaging. And we showed here a lower brain activity in association with the prenatal OP exposure during pregnancy. So this means that for pelagic cohort, we observe no association with cognitive performance with the global intelligence scale, but we observe a detrimental effect on the brain functioning using other tools such as MRI. Okay, so finally in 2020, there were two additional studies, epidemiological studies in the literature, the pelagic study and the home study, which is another North American study. And the home study did not show any association with birth cohort and nor with the cognitive performance. But we think that various results in this literature might be explained by the heterogeneities of our study population. And this was established in a scientific consensus saying that OP are detrimental for the neurodevelopment. So then what do these studies bring for the policy action? So first, in our French context, the pelagy data provided in 2008, providing the first biomonitoring data in the French population concerning non-persistent pesticides. So we say for the first time that all pregnant women were exposed to non-persistent insecticides. So it was a quite shocking result at that time because it was not so common to say that few years ago. So we actively communicate these results in few local organizations in Brittany area. I remember a specific organization which fought for the free pesticide cities. So it was before the law in France that phased out this pesticide use on gardens and on cities and so on. So we think that our communication with them might have provided a new argument for them to fight for the free pesticide cities. Oops, sorry, I forgot. We also shared our experience, our scientific experience in a specific conference with colleagues of Santé Publique France in order to promote and to help them in the implementation of our French human biomonitoring program, which came later, a few years later. And then at the European scale, so this epidemiological literature has conduced to the ban of organophosphorus insecticide in Europe, and especially chlorpyrifos in the 2019. So what did we do? Again, in fact, we just communicate, but we communicate the scientific consensus of that OP was a neurodevelopmental toxicant, not the result, one result of one study. We communicate a consensus, and we did that in the right European agenda. And we did that to different kind of people, public, media, policymakers, and all of them with activists and NGO. They have then made the European Commission aware and convinced of the scientific evidence, the scientific consensus. And so before voting for a possible renewal of the chlorpyrifos on the European market, which was ongoing, the European Commission asked EFSA to provide a specific evaluation, a specific statement for human health. And so a specific expert panel conducted by EFSA in parallel to the classical procedure for the renewal was organized, and they use our epidemiological consensus scientific evidence. And finally, chlorpyrifos was not renewed. That's how chlorpyrifos was banned. It's just a not renewal of the substances. But thanks to the European Commission, thanks to all this communication, we could manage with that. Okay, another example I would like to provide you is about childhood cancer. So in France, there are about 1,700 new cases per year before 14 years old. The most common being leukemia and central nervous system tumors. And for them, role of environmental factors early in life is possible. However, as you can imagine, a cohort is difficult to set up, and it's not currently existing in France because we need a lot of money and a lot of things. So we use case control studies, but in France, it's not like Denmark with a lot of high quality registry, but we have in France, we are lucky to have a high quality one registry on childhood cancer, and which is of high quality, and which allow us to have an important sample size in our case control study. So that's a big advantage to work with registry when we are doing a case control study. So in these studies, we investigated several questions. We investigated the possible role of occupational exposure to pesticides, the living proximity to crops using gene codings, satellite imaging, and so on. And we also investigated the possible role of domestic uses of pesticide products during pregnancy or childhood. And finally, in the last 2 decades, so there were a lot of good quality studies and meta-analysis on these questions, and they were compiled in a collective expertise conducted by INSERM. So an INSERM collective expertise is a work for several years made by several researchers that compile and analyze many studies And finally, that serve as a reference document for policymakers and others. But the main strength of this collective expertise is that we chose to summarize our scientific evidence only into 3 levels of evidence. As you can see here, plus high level, plus average level of evidence, and weak level of evidence, which is quite hard for scientists, but very easy to read for policymakers and others. So for childhood cancer, we had high level of scientific evidence for two types of childhood cancer, leukemia and central nervous system, in association with occupational exposure during pregnancy, and also in association with domestic uses that we made during pregnancy and childhood. I forgot to say that people working on the childhood cancer registry are here today. So this consensus has had important consequences on our national system of the recognition of occupational diseases. For instance, it has led to the creation of a special fund for children exposed to pesticides early in life after parental occupational exposure to offer financial compensation, meaning that today the prenatal period is now recognized by our French system of recognition of occupational diseases. And it's a very symbolic, it's a first step, it's not enough, but we can expect that other actions to protect at least farmer pregnant women might follow. Okay, my last example is a study that we made with a postdoc, Remy, in which we chose to work with an extended list of pesticides, so for which we had information on possible exposure in France, but for which we did not have any a priori for their possible toxicity for child health. So we built this extended list of 180 molecules, among which we could analyze 140 molecules in hair samples of pregnant women of our national cohort health. So hair is a quite novel matrix for biomonitoring, for exposure biomonitoring, and especially for non-persistent compounds, but it has the advantage to accumulate compounds for which we were in contact for several weeks or for several months, for instance. So we found that in this study, most of these molecules were detected at least once in this hair sample, representing various chemical families. So we still found organochlorine, organophosphorus, pyrethroids, carbamates, and a lot of others. And it found also that half of the women had more than 43 molecules in their hair sample, showing that French pregnant women are exposed to a great mixture of multiple pesticides. So to provide you a bit more detail on these results, so among the top 20 most detected pesticides, we found 11 insecticides, 5 herbicides, 3 fungicides. We observed organochlorine, organophosphorus, pyrethroids, insecticides, and we observed banned molecules, agricultural molecules, but also non-agricultural molecules such as fipronil, which was in our domestic product that we use against fleas and ticks, for instance, and also permethrin here, with the highest levels, the highest concentration measured in hair. And then we also observed that half of these top 20 most detected molecules were known or suspected to be CMR, carcinogenic, reprotoxicant, and mutagenic. and most of them were known or suspected endocrine disruptors. So then we studied the association between this air concentration with birth weight, for instance, and we showed association already observed in previous studies, such as decreased birth weight with increasing level of OP. But we also show new associations, new signals, for which we have finally not yet any biological explanation, even a posteriori. For instance, I don't know if someone knows bitter-tanol and its biological mechanism. It would help us. So what did we do with that? So we, again, communicate and share our experience to different kind of people, policymakers, and our National Agency for Health Risk Assessment or biomonitoring. So we know now that the use of hair in the French biomonitoring program is planned, at least it's considered and tested. And we expect to see an extended list of pesticides in this program, but we are not sure that it has yet been possible in this biomonitoring program, but we hope so. And for our association results, we chose not to actively communicate these results, since we consider that these results as still too much exploratory. We consider that we need to accumulate at least some biological possibility before communicating actively these results outside the scientists. Okay, so to conclude, my final key messages is that we need more observational studies on pesticide and child health. The ban of OP has induced, as you could guess, an increasing use of the already existing pyrethroid insecticides. But there is already first epidemiological evidence that show a possible neurobehavioral disorders in association with the prenatal exposure, with the early life exposure to pyrethroid. So we hope that we are not repeating again the story of a regrettable substitution. So we need to work on that. We have also gaps. There are only few data, for instance, on child health or child exposure for the children of the farmer families in France. I could see yesterday that there is some data like that in South Africa, but not in France. We still do not know whether diet contamination has a role on child health, as well as there are only very few studies that have investigated fungicides or herbicides and their possible role on child health. Okay, so we are aware that the place of scientific evidence in policy making is not straightforward, and it's not guaranteed neither. But we have to be tenacious. We have to keep in mind that scientific evidence generate policy actions at different scales. We should not target the European policy action at first. We have also national policy action and local policy actions. And usually local actions are the quickest to implement. So you have to keep in mind that. And my only advice I can do is to, as a scientist, to communicate wisely your results and also how science works. Take your time to communicate that to various kind of people and stakeholders, including farmers, for instance. But just be cautious with some journalists who generally wants to hear a scoop, and they are not here to listen to you how science is working. So I would advise to talk with journalists, some of the journalists, only if you have a scientific consensus or if you are sure that you have robust scientific evidence. So that's it. Thank you very much for listening.
Thank you for very nice presentations, especially the translation from science into policy action. I think it's very impressive what you have accomplished. Are there any questions in the room? Please raise your hands.
I can take a question while we're waiting. Yes, I agree. Very interesting and impressive to see how you've been able to affect policymakers. And on the lines of that, what in your experience has been sort of the most successful practical advice to approach policymakers? How do you do that? How do you go through with a message?
Directly to policymakers, you mean directly?
Yes. Is that what you would suggest? Or, I mean, because you talk about that going through journalists is not such a good route.
Journalists is sometimes quite dangerous, I guess, for scientists. But directly to policymakers, I have no special advice, but my main message is that we need to communicate to people, any kind of people, because people carry messages, then there are activists and NGOs that carries also the same messages, and then the stakeholders, including the policymaker, wants to follow the people, in fact. So this is here where we have the power as scientists to communicate to a lot of different type of people, and especially civil society, in fact. And concerning policymakers within the policymakers, for me, I include our National Agency for Risk Assessment and Safety, for instance, because they communicate directly with politicians. And I belong to several type of scientific expertise group within this national agency. And it's useful for them and for us also, because we discuss of how each part work. And as a scientist, you can say, this is a great signal, so we should do something here to this National Agency of Risk Assessment. And in France, I guess this is my point of view, we are quite lucky with ANSES. ANSES is very aware to hear science, and there are a lot of our previous PhD students who work there, so they know science very well, and they know that uncertainties is not a big deal. So we can more easily communicate with these agencies compared to police stations, for instance. But it's important to, as a scientist in your career, I guess it's important to work with these agencies.
Good morning. Hi, here.
Yes.
I'm Adriana from the Swiss CPH.
Yes.
Thanks a lot for your presentation. It was really nice, and for the whole overview, and for being able to take chlorpyrifos out of the market in Europe. I was wondering whether you looked into differences of people that live close to organic farms and non-organic farms. You find different exposure patterns there. And also, I understand that for the organochlorine pesticides, I would assume that most of them are not applied, that are on soils and highly volatile, and that can travel quite some distances. So I would wondering whether people are also exposed with different patterns there. Thanks.
I expected this kind of question. And what can I say that this is also a personal point of view, is that in science yet, at least in epidemiological studies, right now, we failed to answer question about whether the living proximity to crops is at risk for human health. We failed to find we showed association, yes, of course, but we failed to translate these results to the policy action, because when we look at living proximity to crops, we use our epidemiological standards, we use our scientific thinking, we use, for instance, buffer of 500 meters around the residence, or 1,000 meters around the residence, and we say that if you have crop within this big buffer, you might be at risk. But for policy action, 1 kilometer buffer is too big. We cannot have a policy action with this type of distance, you mean we will lose 30% of our area, crop area, if we say that we should not treat our crop within this buffer. So it's not realistic, I mean. So to me, for proximity living to crops, the best science for now is to do experimental data, exposure data, monitoring data, and probably on a shorter distance with a lot of specific detail according to how we treat. Is it with granules or is it a dispersion of water and so on? Did I answer? Yes, okay.
Okay, in the interest of time, I think we need to continue. Thank you so much, Cecile, for that nice talk. Yes, so now I'd like to introduce our next speaker, Jade Chaker, who is a postdoc researcher here at IRSET-Inserm, and she works with untargeted exposomics of the internal exposome, so working with large chemical data sets and using high-resolution mass spectrometry for this, and also various bioinformatic tools. So you've been developing a specific software to be able to automatically annotate different chemical compounds. So welcome, the stage is yours.
Thank you. So first of all, thank you for inviting me to be here, and especially alongside Cecile. It's an honor. So as you may have heard, I'm not an epidemiologist, I'm a chemist. So as such, today I'm here to talk to you about the non-targeted characterization of the human chemical exposome. And more specifically, I hope to give you conceptual tools to better understand how it's a new opportunity for exploratory research in environmental health, and also what limits there are currently regarding these techniques. So first of all, a little bit of context. As Cecile presented previously, you already know that our exposome, meaning everything that we're exposed to from our environment, from our conception to our death, has potentially an effect on our health. And so this exposome concept is very wide. It encompasses things such as social capital, climate, but also oxidative stress, and more specifically, and that's what I'm interested in my research, is the chemical exposome. So the chemical exposome is in itself fairly complex and vast. There are, for example, 175 million compounds in the chemical abstract service, which is significant. And even if you look only at the European scale, there are 23,000 compounds registered in ECHA in 2020. So if you want to characterize such a wide array of compounds, you're going to have to, well, look for a specific way to do that. Traditionally, what we have been using are targeted methods. What I mean by that is that you will generate quantitative data on a predetermined list of compounds. Now, that's extremely important because this quantitative data is very much needed, first of all, to establish very robust epidemiological associations, but also because we need this quantitative data to be able to go to the policymaker level, as Cecile presented right before. But now we might ask ourselves the question, well, how do we generate new hypotheses to know what compounds to look for? And this is where non-targeted data comes into play. You will generate, this time not quantitative, but semi-quantitative data, but you will not have a predetermined list of compounds, meaning you will be able to look in an exploratory way in what is in a sample that you're interested in. Now, how are we able to do that? Well, one of the techniques that helped us do that is high-resolution mass spectrometry. And what that does is that it can analyze a signal, a chemical signal, with such a precision in mass that we are able to go back to its chemical formula using only its mass. And that was a great advancement in analytical chemistry that allowed us to elucidate the identity of a signal without knowing its identity prior to the analysis. So if I ask, how do I characterize the exposome? This is quite a classical workflow. I'm going to go through it rapidly. You start from an exposure. You want to do an exposure assessment. So first of all, you would take a chemical fingerprint of your sample of interest. Then you would translate this chemical data into a format that you're able to manipulate more easily, so a simple table or a matrix. And then what you will do is, for each feature that is detected in your analysis, you will try to attribute a chemical identity to it. Then you will compare the area of the signal between individuals, and you will generate a report. Today, I'm going to be focusing on these three specific steps because they are the ones on which we are mostly working on. The general objective is to implement a non-targeted workflow based on a specific method. I'll go into it right after that. That is applicable to the epidemiological scale, which means that is applicable at a large scale, which is also a point of difficulty in and of itself. So first of all, I'm going to speak quite rapidly about the choice of matrix. So you have two main routes that you can go. Either you can go to environmental monitoring, water, air, dust, many other things. That's an interesting approach because the sampling is obviously non-invasive for people, or rather less invasive. It's fairly inexpensive. You can have passive sampling, which means you install a sampler and you leave it there for 1 week, 2 weeks, a few months, so that it collects the environment passively. The matrices are a bit simpler to analyze, and it informs on the exposure sources. Where does my exposure come from? Is it from the dust? Is it from the air? Is it from the water, etc.? However, environmental monitoring is an indirect way of measuring human exposure. You would need to add several significant types of data to really understand how we are exposed to the compounds that you find in environmental monitoring. For example, how long are people exposed to this? Are the compounds bioaccessible? How are they? How do they have access to the body? Is it through ingestion, through dermal contact, etc.? The second route you can go is human biomonitoring. For example, using biofluids or biological samples, blood, urine, hair, etc. Here you will have more or less invasive sampling. It's more costly because, for instance, you need people to perform the blood draw or things like that. And it's not always as true, but you have a more, let's say, pointed time at which you do the sampling, and you can't have something on 1 month, or it's a little bit harder, at least. The matrices are also more complex, and you will not be able to distinguish the sources of exposure, which can be harder to translate to policymaking if you don't know what the source of the contamination is. However, the advantages are that it's a direct measurement, and you take the total exposure into account. So you will have a direct link between the exposure and the health effect. Here, I'm going to focus on the human biomonitoring because that's what I do and what I know best. Just a quick word before I go on. You will not see the same things depending on the biological matrix that you choose. If you choose blood, for instance, you will see a little bit more persistent compounds. If you look at urine, a little bit more non-persistent compounds. With hair, it's a little bit of a mix. So be aware that the choice of matrix will impact what types of compounds you are going to be able to see. You also have a second methodological choice that you're going to have to make, is what analytical platform are you going to choose? Even if you know that you start with a blood sample, for example, Well, if all of this triangle is what you would be able to see in a blood sample, the choices you make for collection and storage will decrease what you'll be able to see a little bit. And then how you prepare the sample will decrease it a bit further. And how you choose to profile your sample, what you choose to make the fingerprint, is going to reduce it a little bit more. Here in the squares, you can see the different techniques that you can use. And here I'm going to be focused on the yellow one, the liquid chromatography high-resolution mass spectrometry, which is one of the most used platforms to date alongside GC high-resolution mass spectrometry. With LC high-resolution mass spec, you will see a bit more non-persistent compounds compared to GC. When you're looking to prepare your sample, you have to make a compromise between sensitivity and selectivity. And what do I mean by that is that, for example, in human blood, which is the matrix I work with the most, you have up to 8 orders of magnitude between, in terms of concentration, between some endogenous compounds right here and the environmental compounds that we're interested in. We have something that is called ion suppression, which means that the less abundant compounds can be quite invisible because they are masked by the signal that the higher concentration compounds give. So that means we have to eliminate highly abundant analytical interference, so proteins, phospholipids, etc. But we still want to keep these exogenous compounds that we're interested in. So here I'm going to present very quickly a little experiment that we did to evaluate how the sample preparation method affects what we see in the end. So we took a plasma homogenate and we separated it in 8. 4 of those were spiked at different levels with 50 compounds of various physical chemical properties. And 4 of these homogenates were not touched at all. We prepared all 8 of them and we injected them. Here I'm only going to present the results on cohort samples. And here it's samples from the Pélagie cohort, which Cecile presented. And it was blood samples from 12-year-olds at this point. And here on the top here, you can see PPT and free. Those are 2 sample preparation methods. PPT is protein precipitation, which is the standard, and free is a phospholipid removal method. And here is the log of the fold change for the areas for the same samples prepared by 2 different methods. And what you can see here is that more than 50% of the annotated compounds were only seen with one or the other sample preparation. And even further, around 80% of features were strongly preferentially detected with one or the other. So what that means is that the way that you prepare the sample is going to allow you to see a different chemical space, basically. Here, as you can see, there are compounds that are annotated, but here it's only, I think, about 100 out of tens of thousands of features in the samples, and the proportions were verified at the non-targeted scale. So this is not only true for what we annotated, but overall. So what we suggested in this work is that you can use 2 complementary sample preparation methods in order to enlarge what you are able to see in the samples that you're interested in. The next step that I talked about is the data processing step. So just to give you an idea, we have complex matrices and very low abundant environmental compounds, as I said. This is an example of a chemical fingerprint of a plasma sample. And here are some compounds that I annotated. If you can't see anything, that's normal. That's the point I'm trying to make. And so when we try to translate this chemical information into the matrix that I talked about, we want to make sure that the data processing tool that we use is going to be capable to disentangle this almost noise level signal from the highly abundant compounds, such as here. Here are some phospholipids, for example, that are very highly abundant compared to these environmental compounds. So we took the four homogeneous that I talked about earlier that were spiked with some compounds, and we compared 4 data processing tools, which are listed right here. The first 2 are open source, and the second 2 are from how would I say, the software that were provided to us with the machine that we used for the analysis. And what we saw is when we tried to compare, so detection frequency is out of my 50 compounds, how many of them do I see after the data processing? How long did it take me to generate this matrix? How easy it was to do? How does it do with the semi-quantification? I injected 4 times the same sample. Does it give me 4 times the same area or not? And am I able to see such a small difference between the spiked samples and the non-spiked samples? For the first open source tool, MZMine2, very good detection frequency, almost 100% of compounds were found, but longest computing time, 18 hours for 9 samples. When we're talking about epidemiological scale, it's not feasible anymore. XCMS, I would say, is the standard in metabolomics and exposomics. Very good performance overall. The only disadvantage is there is no graphical user interface. If you don't know how to code, basically, you can't really use it. And as chemists, spoiler, not many of us know how to code. For the vendor software, both of them were quite good in all the areas, with a slight preference to one of them, which is marker view, except on the ease of implementation for one of them, which has a slightly better GUI, but that's not as significant. Overall, what we gathered from that is that using open source software to generate this matrix is highly adaptable. You have many parameters on which you can play a little bit, and it's fairly transparent, but that means you have to have expertise on what these tens of parameters mean. You can't just change them kind of blind and hope for the best. On the other hand, vendor software is very relevant for high throughput application. If I come back to the computing time, you can see these 2 little dots. It's less than 2 hours, which is what we're looking for when we are looking to go through thousands, hundreds, or thousands of samples. But overall, we still need improvements regardless, because even MZMine2, which came the closest to 100%, did not reach 100%. So we still need a little bit of improvements for compounds that are closest to the baseline, that looks closest to noise, basically. Now I'm going to go through the annotation steps, which is linking chemical features to chemical identities. So this is what you get out of your data processing step. You get a list of features. A feature is a line. It has a mass, a retention time. Those are analytical parameters, and an area related to each sample. And you want to link potentially tens of thousands of features with chemical identities. So as you may imagine, you're not going to do so by hand because it would take quite a bit of time. But you have basically 2 main strategies. The first one is de novo annotation or non-targeted annotation. You already have your health outcome of interest, and so you would have patients in group A, group B, group C. You would compare the areas between them. You would prioritize features of interest, and you would annotate them specifically. The second strategy is suspect screening. So you have a list of compounds that are of interest to you for various reasons, and you can match in an automated way your chemical, your features, to your suspects using chemical predictors. Right now, I'm going to focus a bit more on this strategy because, as we said, we have developed a software that does precisely that. This software is called Scannotation. It was published a few months ago, and also, okay, here is the front page. It's very pretty, and it's available on GitHub if you or any collaborators are interested. So how does it work? What it does is you will have a list of suspects, and you want to get to a list of pre-annotated features. And how do you do that? Well, you will do a first filter on the mass to charge ratio, or the mass if you want to be a bit more colloquial. As I said, this relates to the chemical formula. So first of all, you want to make sure that you have the right chemical formula. Then you filter on retention time that is linked to physical chemical properties of the compounds, and that will give you a bit more information of, for instance, if it's polar or not polar or a little bit in between. In our software, you can have an experimental retention time, which is great if you have the standard, but if you're in a case where you don't have the chemical standard, for example, you're looking for metabolites that are not available on the market, you can also predict a retention time using varied tools. We also filter on isotopic fit, and why we're interested in it is that it allows us to discriminate compounds based on their chlorine, bromine, and sulfur content, which are often indicative of bioactive compounds, or not all compounds that are bioactive have these atoms, but usually the reverse is true. And what is not yet implemented, but is our next step, is the MSMS profile, so fragmentation profile. So a molecule will break itself in very characteristic patterns. And for now, we're doing this comparison manually, but we hope to add it to our software fairly soon. The idea behind the software is to score every single filter that we have with confidence indices between 0 and 1. So 0 means there is no similarity at all, and 1 means perfect similarity. It is the same. And with a global confidence index, the user can see in one indicator if the feature and the suspect are close or not. So the results look a little bit like this. Here are some identifiers. So the name of the suspect, it smiles, which is a universal identifier, its chemical formula, and all the confidence indices that I talked about are right here, with the global confidence index being right here. As you can see, these are quite high. We also have to perform the manual curation on the fragmentation profile, as I said earlier. And just to give you an idea of the timing, this takes a few minutes, and this can take tens, hundreds, thousands of days, depending on how dedicated you are to it. So clearly, this is, as of now, the biggest bottleneck for generating new hypotheses using non-targeted approaches. Sorry. Okay. The idea now is to link these suspects with the corresponding lines in the data matrix that I presented to you earlier, and to use the areas in each sample to link environmental exposure to health data. For example, neurodegeneration index or any other health outcome that you're interested in. So some results from our software, I talked about the spacking assays. The processing time was very short. 100% of peak-picked compounds were correctly pre-annotated with confidence indices that were quite high. So that means that our indicators were relevant. And we also did an assay with the Norman network, which is a European network. We had a mixture of reference standards, and we had the best score out of 16 European laboratories, with 22 of them correctly identified, with also high confidence indices. Now I'm going to talk about two large-scale applications. The first one is the Pélagie cohort, which Cecile already presented, so I'm not going to present it again. I'm just going to say that we took 125 blood draws from adolescents, We prepared them with the 2 sample preparation methods, and we tried to annotate them. Oh, sorry, that's my mistake. That's the old name of our software. So we compared 2 different softwares for the annotation. As you can see, we had some overlap between them, and we tried to understand why some of them weren't annotated by the other software and vice versa. The ones that were only annotated by our software had, for the most part, the issues of no fragmentation data acquired. Sometimes the chemical signals are so low that the machine isn't able to generate a fragmentation spectra. And with traditional tools, that means that you aren't able to give this signal an identity. But since we're focused on mass, retention time, and isotopic pattern, we were able to do so. For the 11 compounds that we weren't able to annotate, it was because, simply put, it wasn't in our initial library, which, good news, it can evolve. So that's only an issue for the first pass, and then you add your compounds to the library, and the second time you won't have this issue. This is a scale that is traditionally used to translate confidence in the annotation. Level 1 being, I am sure that this is this compound, and level 5 being basically, I have no data to prove that this is the compound. When you don't have MS2 data, when you don't have fragmentation data, you're stuck at level 4, which, especially for policymakers, is no bueno. However, sometimes you can have strong evidence that this is still your compounds of interest. For example, you have a good isotopic fit. Here is the example of triclosan glucuronide. Great isotopic fit between theoretical and the sample. You have other metabolites for the same compounds in the same sample. And you also have the neutral loss, which is fairly small here, I apologize, but which means that structurally it is a strong hypothesis. And also you have the retention time, which is coherent with predicted and experimental. So that means that you can have a body of proof that we can use to try to adapt the standards to communicate confidence in annotation when we're lacking this specific type of data. Okay, so enough about the software. Let's talk about the samples now. We had a large coverage of the chemical space. We could see food-related compounds, health and personal hygiene-related compounds, also industrial compounds, pesticides, etc., plasticizers, gut metabolites also. We saw the usual suspects, everyday pollutants, phthalates, parabens, perfluorinated compounds, also fipronil sulfone that Cecile talked about right before, and also emerging pollutants, such as a terephthalate in 86% of our samples. We have no toxicological data on that, so we don't know if it's a problem or not. Also acesulfame and aspartame, which are food-related compounds in 97 and 100% of compounds. We also have little data on their impact on the metabolism. And to finish off, the physical chemical characteristics of the compounds that were found were very diverse, which means that you can indeed, with non-targeted approaches, characterize a wide array of chemicals, maybe even wider than what we expected. Lastly, for this application, we discovered a new biomarker of interest. So here, the small pink peak here is bromoxynil, which is a pesticide. And here is a bromoxynil metabolite that we named MP11. Bromoxynil is a herbicide detected already in pregnant women in Pélagie. So we asked ourselves whether we had long-term exposure here. And also, we found that this metabolite was detected in 97% of samples, whereas the parent compounds was detected in 61% of samples. And also, the area ratios, as you can see, are between 3 and 8. So we can then ask ourselves, can this be a new biomarker of interest to characterize exposure to bromoxynil instead of looking for the parent compounds, as is done so far in the literature? Okay, so little issue with, okay, it's all right. The second large scale application is the Eglantine project, which is on exposomics and dementia. So what you can't see behind there is basically around the life of an individuals, you can have a faster than normal neurodegeneration, which has an impact on their everyday life. And we know that some factors of dementia are genetic or non-modifiable, age, biological sex, ApoE epsilon 4 variant, etc. But there are 12 modifiable risk factors to which we attribute around 40% of the risk. Some of them are psychosocial, cardiometabolic, lifestyle. And so we can ask ourselves, what about other environmental chemicals? The 3-city study, which encompasses around 9,000 adults of more than 65 years old at inclusion, was created to have this kind of follow-up of cognitive function of older adults. And we also have neuroimaging data, which we are both going to use in the context of the Eglantine project, for which we have blood samples of 518 people at inclusion. And for 109 of those patients, we also have blood draws at 4 years and 10 years later. And we are evaluating their internal chemical exposome in a targeted way for some compounds and non-targeted way for other compounds in order to link it to brain aging with the endpoints of cognitive decline and cerebral atrophy. The two objectives of the project is, first of all, to characterize the chemical exposome using the targeted and non-targeted methods, and also at inclusion and with the exposure trajectories, and then, of course, associating this with brain aging. A little bit of chemical talk. I promise I'll be quick for this. What you see here in reds and yellows are quality control samples, which are extremely important. It allows you to make sure across your sequence that the first sample is comparable to the last sample. And that's extremely important in non-targeted data, because how are you going to check whether you're losing signals or not? You have to have very strict quality control procedures. So for one sequence, we have 3 blanks, 39 QCs, and 92 samples. So it's quite a good ratio, I would say. And for the Eglantine studies, that means we had 8 batches per mode of analysis, which is 92 times 8 is 736 samples. This is the system on which it was acquired. It's not very useful to you, but just in case you're interested, I've listed it here. Here you can see that I mentioned spiking. The idea behind this quality controls is, first of all, to look at whether one sample is repeatable, but also if I spike my samples at very low levels, 2 nanograms per milliliter is extremely low, am I still able to see them from the first QC injection to the last QC injection? Do I lose sensitivity? These 40 spike compounds are, of course, chosen to be very diverse in physical chemical properties to represent the variability of what you can have in your samples. And of course, you will do those QA/QC verifications. So even if you're not familiar with the values these have to be or would have to be, just know that it worked. If I go back to my 40 spike compounds, you remember how I told you you have to also do QA/QC on your data processing? Well, that's exactly what we're doing. So basically, if we look at the features corresponding to the spiked samples, we're looking at, for example, here I took the QC spiked at 20 nanograms per milliliter just for an example. You would look at the specific columns related to these samples, and you would check, do I still see a signal? Is the area repeatable or not? And that allows you to check, first of all, that your chemical analysis went well, and then that your data processing went well as well. And good news, it's good as well. As I mentioned, these QA/QC for data processing were published in the context of the PARC European project task 4.3. And what we propose in there is to evaluate all of these parameters to encourage scientists to ensure that their data processing is not affecting their results. We also created a specific library for this project. The review that was used is also published. I already had in lab a library of around 6,000 compounds, which is potentially in plasma or serum from various sources in the literature, so papers, databases, etc. And with this literature reviews, we added 183 compounds with documented effects on neurodegeneration. 38 of them were not added to the library because, as I said, when you choose a technique, you will inevitably lose part of the information. And with the technique that we use in the lab, we can see metals, we can see PCBs, we can see HAPs, et cetera, et cetera. So that left us with 145 compounds, and we were a bit happy to see that 92 of them were already in the library. So the first library was not so bad, but we were able to add several compounds, and especially, maybe it doesn't speak to you, but as you can see, you have a molecule and an additional word, and usually that means that these are metabolites, which were not initially in the library, but they were proven to have an effect on neurodegeneration as well as their parent compounds. So now we're looking to go to the second step, the second objective, the association between environmental exposition and brain aging. And maybe in a few years, somebody else than me will present these results at a future ISEE, I hope. So just to conclude, give you a few take-home messages. Non-targeted approaches are very complementary to targeted approaches. They have the goal to generate new hypotheses and not at all to replace what can be done with targeted approaches. This is helpful to identify new chemical risk factors, in the occurrence of chronic disease, and the visible chemical space highly depends on the succession of methodological choices that you make throughout your process. So if you want to do a non-targeted characterization of the internal chemical exposome, you can help it be more exhaustive by optimizing every single step of the workflow. And you can help it be more efficient by developing new innovative tools. And of course, it's applicable at the epidemiological scale, even if we're at the very beginning of it. So I would like to acknowledge everyone that has contributed to this work, and especially the Elixir team, which has worked very hard for this ISEE edition. And thank you for your attention.
Thank you so much, Jade. That's really, you explained this quite complicated technique, but in a very clear way, I have to say. So I really appreciate that. And it's nice to see how you're really moving the field forward also. And it seems like there is a lot of work to be done also going forward.
Yes, there is, for sure.
So you're going to have to talk with some of the epidemiologists in the room here. So we have some time for some questions. So please raise your hand if you have a question, and we'll have a mic out. We have one here.
Thank you very much for your very comprehensive, nice presentation. I have a question on the level of annotation.
Yeah.
So, like, what's the difference between like level 1, level 2, level 3? How can we reach level 1?
Okay, I'll go back to the slide. Hold on. Maybe I can do it a bit more efficiently like this. Okay, so I hope you can see. Okay, So here are, on this column, are the minimum data requirements to be able to qualify at every level. So exact mass of interest, that means that you only have the mass. That means it's not even a formula yet. So basically here, you know nothing. You just have a mass, it corresponds. Okay, that's great. If you have a bit more information, then you can qualify to say, okay, I have an unequivocal molecular formula. But if you type any molecular formula in PubChem or any database, you can see that for one formula, you still have tens of thousands of possibilities. So right now, the general consensus, what we're using to discriminate between these are MS2, which is fragmentation data. So this is great in metabolomics because when you're looking at endogenous compounds that are very, very highly abundant, you try to fragment them, you have a very nice pattern of fragmentation, very clear, usually very pure. But when you're looking at these teeny tiny signals, sometimes you barely have enough to detect them. And so you're not going to be able to fragment them. So in exposomics, if you use this standard, you're stuck here half of the time. And a level 4 basically means nothing. It's already difficult to be taken seriously with the level 2, because if you have no standard, it's like, okay, it's a level 2, but there's still a bit of uncertainty linked to that. So imagine what it's like at level 4 out of 5. It's clearly not enough as of now, using the standards that we have now, to say, I'm at a level 4, please take me seriously and understand that this is maybe a compound that is of risk for human health. So we're trying to work on new ways or new information that we could incorporate to this standard that may allow us to, how would I say, to climb up the ladder and have at least a comfortable level of information, especially when you have all this body of proof that shows quite strongly that the compounds that is stuck at level 4 is most definitely this compound that you annotated.
Yes, thank you very much.
Thank you.
Please raise your hand if you have another question. So I suspect this technique is being used in multiple different centers. Do you have how much because it seems like the fact of somebody identifying a compound is useful for everyone else.
Yeah.
So how much communication and collaboration is there in this field?
Yeah, there's quite a lot, fortunately. That is very good for the science in general. Okay. As you can see here, I cited the Norman suspect list exchange, for example. Sorry, you can't see right here. The Norman suspect list exchange. So Norman is a European, how would I say, a savant society, let's say, at the European level. And what we're working on, they're mainly focused on environment, but they are slowly starting to encompass human biomonitoring as well. And here there are spaces where you can give all the information that you have regarding compounds, and they are compiling this suspect list exchange, which as of now is several hundreds of thousands of lines long, of compounds with various physical chemical data, and even toxicological data sometimes, prevalence data sometimes. It's a big collaborative effort that we are using to kind of make it easier for everybody to have comprehensive suspect lists depending on their area of interest, because it's not very relevant to have all 100,000 lines in your suspect list if you can't see 3/4 of them just because of the method that you're using, for example. So this is a collaborative effort. And also, of course, all the European projects work at large for making it easier for everyone, or at least to help everyone harmonizing not their methods, because we still want to be complementary to each other, but at least how we evaluate our methods, which is something that is missing so far in non-targeted, because if you want to see everything, you can check everything. It's not possible, contrary to targeted methods. So there is still no standard to evaluate the perimeter of a non-targeted method. And that's what we're working on at the European level.
Thank you so much. So I think our time is up, and I would like to give an applause for our two keynotes. Thank you so much.